chapter 30 here real quick. Okay, so slideshow, here we are. Okay, so nuclear fission, like I just said a second ago, we do actually have nuclear reactions that happen around us from time to time. They are not nearly as drastic or nearly as big. And they're not very common because we are mostly dealing in our atmosphere with stable elements. It's not very often that you are hanging out next to depleted uranium or uranium cores in general. I imagine very few of you have been to Chernobyl at all. What you're looking at in this particular case, then let me finish that thought. That nuclear reactions on the scale of macro don't actually produce that much energy. We don't have to worry about them too much unless they deal in a chain reaction. So what you're looking at here is nuclear fission, and it's what they found. It's what in the video the other day. What's her face? Darn it! I'm gonna forget her name. What's that? Lady. Yeah, sure. I should know her name, but goodness, what was her name? Darn it, I'm gonna miss me. I just had it for like a brief second, I lost it. Okay, so what she was talking about in the snow, right? That they had split and they found radium in the example, and that had been coming off. Okay, nuclear fission typically is going to come from we're shooting a neutron into uranium 235 atom, okay, which is not stable but more so. And of course, you get an uranium 236 atom. You put another neutron, making it more unstable into that element. And what comes out is a lot of possible options. There is two daughter cells, which we are going to call X and Y. These are variables because there are different possible options here, and extra neutrons. Specifically, we'll talk about how many in just a second. Okay, like in this particular case, one possible option is I shoot a neutron into 235, and X and Y are barium and krypton. Okay, two smaller elements that are both stable. But most importantly, in this fission reaction, we have three neutrons being shot out as well. Well, if it took one neutron to take one 235 atom, to 236 and to split and release energy, guess what three are now about to do?
A lot more.
Well, they're going to do three more. And if those do three, and those do three, and those do three, keeping in mind this has happened in fractions of a second, we are going to be dealing with an exponential amount of energy coming out. That small amount of energy that I talked about for one single nuclear reaction right here is no longer small. Okay. And you can do the math on this. You'll notice that the mass numbers add up. We got 236 on the left side. We got 236 on the right side. Notice that the three of those are right here in the neutrons, and these are just reactions like you were messing around with last chapter, just making sure that the same are on both sides. And the Q value of this particular interaction is 200.422 mega eV. What does that Q mean? What does Q mean just happened in this interaction?
That's energy released.
That is energy released, because what about, if I measured the mass of both sides, what would we find? What's that? They are not equal. Which mass is smaller?
The right side.
The right side. The mass is smaller than what it was originally. So where did the extra mass go? It went into energy. Correct. That's what that Q value tells us. So here's a picture of essentially what happens. We have before fission, the neutron comes in, makes 236, making it that little star right there, tells us it's unstable, forms an oscillated kind of liquid drop there, and then they split apart, and you get a X atom, you get a Y atom, and you get three neutrons going off to possibly start this process even further. And nuclear reactors, of course, are attempting to do this in a very stable environment. So you get uranium, and like I said, it's not only barium and kryptonite. Kryptonite, is that right? I will figure this out. Yeah, it is krypton. Yeah, it is not kryptonite. That is not a thing. That's right. I always mess that. And Ba is. Did I say that right? Yeah, it's good. Okay. So you'll notice over here on the other side, we got neodymium and serbium, I believe is what it is, uridium and iodine. We have xenon and strontium coming off. There are a lot of different combination of elements that could potentially come out. Some more likely than others, but the most important thing that you're noticing is that 3 neutrons come out. Now, if this rapidly happens, this is, of course, the general principle behind the nuclear bomb. Now, obviously, we do not want a nuclear bomb in our nuclear power facilities. We just want to maintain a good amount of energy that's specifically coming off of this. Okay, so what they do at nuclear reactors, okay, is they have this nuclear reaction, but inside of it, we have fuel elements. These are the things in red, aka this is your uranium 235. Okay, or there's other elements that can potentially be used, but and then they have these guys called control rods, and the control rods are stuck down in, and what they are is an element that naturally absorbs neutrons. Okay, and kind of the further in you put them, the more neutrons are then going to be absorbed. So the idea is, out of these 3, and by the way, it's not always 3, sometimes it's between 2 and 3, but let's say it is 3 every single time, these control rods are meant to let this build up, to basically let this reaction take place for a very small amount of time, so we're building up energy, and then start to absorb 2 out of 3 of the neutrons. Okay, why? Because at just 1 neutron going to the next, now you're just going 1 atom, and basically it's just going to simply maintain. It's going to maintain the energy production that it's currently at. So this right up over here is a measurement of the reproduction constant K, and simply K stands for how many neutrons are coming out. Okay, K is 1 is critical. Now, despite how you and I might feel about the word critical, this is actually a good thing. This is a very positive thing. Okay, when a nuclear reactor is running critical in all the movies, that means it's terrible. Things are really bad. Actually, according to its definition, it means it is running correctly. It is running efficiently. It is at 1. K equals 1 is exactly where you want to be. You're putting out production of energy and maintaining that. Okay, you would have somebody monitoring this on the regular. Okay, in addition to obviously also having computers monitoring this exact process that are helping with the control rods coming in and out. But you definitely have someone. This might be, in fact, what Homer Simpson does at the nuclear power factory. But of course, that's a cartoon. So K is less than 1 means you are absorbing way too many, and that means it is subcritical. It means that the nuclear reaction is overall then dying out. Okay, and of course you can do this if you want the nuclear reactor to turn off. Okay, you can put those control rods completely in, absorb all the neutrons so that the reaction entirely stops and keeps things safe. Supercritical is bad. Yeah, that means it is above 1. Now it will stay above 1, like I said at the very beginning, to kind of raise to a particular energy production level where they're happy with it, and then they want it to be K equals 1 just to maintain. Does that make sense? Okay. All right, let's talk about the sun. So you'll notice in the last slides, I actually kind of switched very quickly. Where's it at? Nuclear fission. Okay, you might have heard fission and fusion. Okay, essentially these are very similar processes. We are just mostly looking for a positive Q value for energy to come out. Okay, fission is where you take big elements and make them small. Yeah, so your nuclear bonds, pretty much everything that we know how to do is fission. Okay, the next one, the sun, is fusion, meaning it is taking lighter elements and putting them into larger elements. The main difference in the problem fusion is incredibly productive and incredibly cheap in the elements that it comes out with. Okay, the problem with fusion, does anybody know the problem with fusion versus fission as far as our ability to use it?
It takes a lot of energy to start.
Close. You're not wrong, but not quite what I'm looking for. It requires an incredibly large temperature in order to pull off. So right here, as we're looking on the page right here, you're noticing that fusion in the sun. I don't know why that second line is not actually animated because it should be, but that's all right. So it basically, the way we understand it, the fusion in the sun takes place in three particular processes. Okay, so the first is you have 2 hydrogen forming what's over here, a deuterium in beta decay. Okay, that's a positron right there. Remember, the positron comes out with the neutrino, and the electron comes out with the antineutrino. Okay? And then the second line right here, we actually have hydrogen and deuterium, the product from this last guy. So ultimately, it all starts with hydrogen. Hydrogen plus that deuterium that we just gained from the last one is going to give us what's called helium-3. I believe, what is the name of that? I want to say it's not heavy helium. I know that's not right because it's not heavy. Pull it up real fast because I want to make sure to name it correctly. Yeah, energy thought in sun is called the proton-proton cycle. In this cycle, 4 protons combine to form an alpha particle and 2 positrons, and 25 mega eV of energy is released. The first 2 steps are shown up there with DV and deuterium. Okay. The second reaction is followed either by a hydrogen-helium fusion or helium-helium fusion. The liberated energy is usually carried away by gamma rays, positrons, and neutrinos. Gamma rays are usually quickly absorbed by dense gas, which raises the overall temperature. The positrons combine with the electrons to produce gamma rays, which are also absorbed by the gas before they travel more than a few centimeters. The neutrinos, on the other hand, never interact with matter, so they escape from the star, carrying about 2% of the energy generated with them. This energy-liberating fusion is called the thermonuclear fission reaction. Hydrogen bomb, first exploded in 1952, is an example of an uncontrolled thermonuclear fission reaction. And obviously a great deal of effort is underway to develop a sustained controlled fusion power reactor. Controlled fusion would be called the ultimate energy source because of the availability of water, its fuel source. For example, if deuterium isotope and hydrogen consisting of proton and neutron were used as fuel, 0.06 of a gram could be extracted from 1 gallon of water, costing about 4 cents, meaning that fuel costs, even in an inefficient reactor, would be almost insignificant. The additional advantage, of course, would that very few radioactive byproducts are formed in that particular process. So yeah, so you have hydrogen, 2 hydrogen into deuterium, hydrogen plus deuterium into helium, and then you either have hydrogen and helium-3 into an alpha particle plus, once again, positron and neutrinos, or you might have 2 heliums into a alpha particle and actually back into 2 hydrogen.
What is the little, I think it's the gamma symbol, what does that stand for?
Gamma stands for gamma radiation. This is gamma. These 2 are not gamma, those are nu. Okay, it's the Greek letter nu, and they stand for neutrinos. Okay. So most. What's that?
E2 to positive is like a positron?
That is a positron, yes, correct. That is a positron that leaves these fusions up. Okay. Fusion reactors. A possible option here in the future would be we could turn, like it says, deuterium into helium. Look, I'm not going to go over all of these right now because it's kind of a moot point. Basically, what you're going to see is, and you can look up all of these isotopes on that chart that was already given to you, and you can calculate the Q values to see that they definitely do produce a good amount of energy. Okay, this right here is an idea. It's called the, I think you actually might be very interested in the name of this hypothetical thing that they are attempting to come out. If I remember correctly, no, I'm sorry. I thought this was the Tesseract. This is not the Tesseract. This is the tokamak. Tokamak is the name of this hypothetical thing here, but I'm not going to talk about it. That's all. Excuse me. Theoretical, and we don't need to get into it right now. So, almost done here. The next slide is going to probably make you chuckle a little bit because of how much time it's been since you actually learned it. This is where the textbook wants you to learn it, but I apparently decided that you should learn it a lot sooner. So hey guys, if you didn't know already, there's 4 fundamental forces. There's a strong force, that's where the neutrons and protons are bound in the nucleus. There's the electromagnetic force, which binds atoms and molecules, that's the attraction between positives and negatives. There's the weak force involved in the mechanism of beta decay specifically, okay? And then there is a gravitational force that holds planets and stars and galaxies together. That's you've heard of gravity before, but that's crazy. Okay. Now we are going to briefly talk about this, just out of more curiosity than anything. The elementary particle and the fundamental forces. So, firstly, how do these forces? what's been found about every single one of these forces is that there is actually a particle traded back and forth between this particular process. Now, the second one up there would probably be the most obvious to you, meaning, okay, hey, I've got a proton over here, okay? What does it put out that will affect a proton over here? What do we usually say? Hey, there's a proton here, it popped into existence, what does it put out? Before that, what would we say back in electricity? It's a proton that just popped into existence, what is it going to do? What's it going to put out?
Charge.
Big E. Big E, what is it? Electric field, yes. Electric field's coming out. And how fast does electric field go?
Speed of light.
Speed of light, right. And so if there were two positives, okay, and not that this could happen because of conservation of charge and mass and all that much jazz, but like watch here. Let's say this positive popped up into existence, okay? Would this immediately be affected?
Yes. Wait, no.
No, not immediately. How much time would it take to get affected? Well, we would take this distance and divide by c, because that's how fast the electric field actually travels, right? Now, another way to look at light is, as what you were saying a second ago, you're going to skip ahead of me there. What is actually electric field? What is actually traveling in this particular thing? It is photons. Photons that are traveling back and forth between one another. So whether or not they're kind of repelled or attracted or that type of thing. Anyway, every single force up there kind of has its own individual particle that kind of trades back and forth. Okay. Now we are definitely heading more into the theoretical here. Okay. But I don't want you to look at the theoretical and entirely go like, we don't know this. This is all make believe, because there's a good amount of research behind all of these, even if I'm not super familiar with them. So the interaction between protons and neutrons with strong force is with gluons. Kind of makes sense. Okay. Photons with the electromagnetic weak force are W and Z bosons, and the gravitational force is known as gravitons, the particle that is traded back and forth in order to experience these particular forces.
What are bosons?
It is a fundamental particle. Without it is the particle that trades back and forth. We force. I mean, honestly, that's the best. That is what it is. So like, I don't have a better explanation for it. Okay, what you're looking at right now here is known as a Fermi diagram. He did these back in I think 1970, so we're getting much closer to where we exist right now, and it's what he showed in the form of how these interact with each other. What do two electrons do? Two electrons repel. What you're looking at right up there is the trading back and forth of the virtual photon. Now, why is it called a virtual photon? Well, because it would immediately be repelled, I'm sorry, not immediately, but very quickly be given and then also received by each of the other ones, affecting their particular distance. Okay. We've actually already had this conversation as well. Which one of these is the strongest? Notice that its relative strength is 1. Okay. How much weaker is electromagnetic? Surprisingly, not as very. It'd be about 100th of the strong force. Okay. Which does make sense because the protons are pushing outward, right? And the neutrons are pulling inward, and they kind of get into equilibrium, so the nucleus can exist. But you will notice over on that that third column right there that it says that electromagnetic force is long, meaning that it's affected by the R-squared rule, or like from, it's a very large distance, whereas the strong force is relatively weak. It's actually at about 1 femtometer before it entirely falls off. Weak force is also, it's even a shorter distance, and it's weaker than electromagnetic and strong. It's about, let's see, -6 there means that the weak force is about what does that be, 1/1,000,000th of the strong force. And then you look at, poor gravitational. Nothing close to the other three up there. All right. So you're looking at gentleman right there. I can't remember his name. Fantastic mustache though. So you're looking at positrons and other antiparticles, and antiproton and antineutrino positrons, right? Antiproton, antineutrino, antipositron right there. Those little lines usually above on those top two indicate that they are the antiparticle, or in the case of the positrons, just the one with the opposite charge. Okay, they're used all over the place. Okay, so hadrons. I don't think you're going to need to know much of this, but I will cover some interesting stuff right here. This gets really out into like I said, stuff that's a little bit beyond us. Now you asked a second ago which particle was. Remember, remind me.
Gluons.
What's that?
Bosons?
Bosons. Bosons are right. Where are they? I thought they were up there. These are all the categories that are up here. You remember us talking about muons when we were doing muon interactions? That's right up there underneath the electron. All of them have a neutrino version. So you see the electron neutrino, the muon neutrino, the tau neutrino. Okay, all of those are those are in the lepton categories. Going down to other ones that you'll note specifically is that a proton and neutron are over here in the baryon category. You can see their rough mass over here on the right side, but it's all in terms of energy. This is that like close to that 931.5, a little bit above it, because of course it is not in the atom itself, which is where U is typically calculated. Okay. I'm trying to remember if there was anything I wanted you to kind of see in this. Yes, I think there might be something that you have to do, and it's just basically, all right, so there's the law of conservation when it comes to these guys, and all I'm just going to simply say is that you have to follow the baryon numbers and the electron-lepton number, which are on this chart right over here. Okay, so the baryon number is right here. Okay, it's either 0 or +1. Okay, the lepton numbers are going to be like right over here in the form of electron, mu, and tau. Those are just the L's right there. And it needs to be, so if we want to see if an interaction is correct, for example, okay, what we're going to do is we're going to take things like this. We're going to say, hey, I told you the other day that a neutron, okay, that a neutron can produce a proton and an electron. Yes? Okay, so let's follow conservation of baryon number. Okay, a neutron has a baryon number of 1, right? An electron has, sorry, I did neutron first. I'm going the wrong way. Where is it at? Okay, so neutron has a baryon number of 1. Proton also has a baryon number of 1. And the electron has 0, and the, what is it? Where'd it go? Where's the other one I need? The electron neutron also has 0. So it's 1 on both sides. It's good to go. Okay. I think you might be given some equations here and asked to check whether or not they are vital or not. Okay. Or the next one. That's right. Oh, and then you should also do conservation of the electron-lepton number. So we go over here and we go, okay, back to the same one. Neutron again has an electron-lepton of 0. Okay. So the total better be 0. So we have the, where did it go? Proton is 0. The electron, oh, let's screen this up then, because I feel like they should be, oh, that's what it is. Okay, the anti, oh, it's literally got it right beneath me, that's dumb. Okay, the anti is always going to be the opposite of that particular number. Okay, so the electron neutrino on this second line right here has +1, but the anti is always -1. Does that make sense? So the total lepton number has to be 0 because the neutron is 0, right? The proton is 0. The electron is 1. So this has to be the anti-neutrino electron -1 for a total of 0 on both sides. Just conservation. And then, like I said, baryon is really easy because it's 1, it's 1, it's 0, it's 0. Does that make sense-ish? Kind of look at the chart, make sure the numbers are the same on both sides. There you go. So you could look at this. I'm not going to make you do it right now because we're running out of time. But which of these cannot occur? You would look at both of those conservation laws. Then there's also conservation of strangeness, which, as the name suggests, gets very weird. The 8-way fold, the quark model. I will talk about quarks real quick because I know you have heard of them previously. Quarks are this idea of build up to other things and also kind of explain that thing I said earlier that a neutron can break down into a proton and an electron. How so? Well, if you look down here in the bottom right, the neutron is an up, down, down. Okay, so not quite. And the baryon is an up, up, down. Okay, specifically, and the color actually weirdly matters of these. You'll notice that the green down over here on the bottom right of the neutron switches to an up in that particular case. And where's the electron? Shoot, I can't remember exactly where the electron is is not up there, but essentially through these switching from down to up, that's how the electron leaves. As the electron leaves, switching down to up, that's where you get the proton coming out of the neutron, specifically the quark sector. All right, and then just because it's kind of interesting, nothing more than that, we've talked about the weak force, but we've not really dealt with it. The electroweak theory of the Standard Model is the weak interaction is very important because it governs the basic stability of particle matter. It's what decides whether or not something is stable or unstable. Okay, so you get essentially, specifically in beta decay, it explains what gets how much energy these neutrinos get in order to balance it out versus how much in the top case the positron gets, or in the bottom case that the electron gets.
Question: what is that K to the 0?
K to the 0, I believe, is a kappa particle. You can see it right over here.
Kappa particle?
I believe you can see it right. No, it's a kaon. Sorry, kaon particle. Yeah, I feel like to a certain degree you're sitting there, listening to me, and it sounds like I'm just speaking, sci-fi, which to a certain degree I am, because this is definitely a little bit beyond me as well. Oh, there it is. There it is. Hold on. The electron has the quark of, yeah, maybe it's not on this one. Because you see up here that the quarks that make up these guys have up, down, down. Sorry. And so, how do you get the electron? The electron is, maybe it is just negative E by itself. I can't remember. It's been a minute since I've done all this. But if you're interested, definitely suggest you read all that. But that's all I've covered. I mean, if you look at the homework real quick, just so we can kind of get a sense of like, okay, great. Great. So yes, there's only 11 problems. This is going to be due Friday, on the day of the homework. Day of the quiz, rather. Quiz will be over chapter. I don't think there is going to be a problem section. There's not going to be a problem section up on WebAssign like it usually is. There will be a problem section, but please understand you're going to be writing a lot of the equations. Okay, so make sure that even on the homework online that you're just practicing that. As long as you can do, so like writing the equations the other day where I said like, okay, if this alpha particle comes out, what particle is going to be left? Like that type of equation. So please make sure that you are certainly able to do that. But yeah, let's just focus quickly on what the homework will look like.
Fusion.
And
Last night you sent me back to chemistry.
do what now?
Last night I got sent back to chemistry
How so?
with all that,
Why does it want me to be out?
all the like, oh, this thing comes out. What's its
Yep.
leftover bits?
Yep. I mean, that's essentially, I told you at the very beginning of this class that high-level physics and chemistry are the same thing. Meitner. Her name is Meitner. Her last name is Meitner. Meitner and Franz, I forget his name, but that's probably better. Alright. Chapter 30, nuclear energy and elementary particles. Just so you can feel at ease. Look, I mean, like you can see like number 1 here real quick. Boom, find the energy released in a fusion reaction. What is that? That is just the Q value, right? So that is the difference in mass, find Q, just like you have been. Photon gets produced in the proton antiproton according to this particular equation. What is the minimum possible frequency of that particular photon? Once again, what you're looking at there is, hey, how much mass do these guys have over here? Because what's the mass of the photon? What is the mass of the photon? 0. There is no mass of the photon. So if the photon produces 2 protons, it produced entirely an amount of mass from nothing. So what had to happen? The energy from the photon gets put into that mass. So you can find then the energy, just kind of basically converting from that mass to energy with that 931.5. And then converting that energy to frequency. What equation do we have? Energy to frequency? The energy of a photon is equal to
HF.
HF, correct, there you go. And then what its wavelength is going to be, real basic C over wavelength there. Yeah, I think that you're going to get a lot of this stuff pretty easily. I mean, once again, number 4 is similar to number 1. Number 5 similar to number 1. Number 6 similar to number 1. Number 7 is like literally like walks you through that. So there you go. And then there's a handful of multiple choice, but I think you'll be good from there. Read the book and you'll be all set. Try to make it relatively easy here at the end. All right, so I'll let you work on homework for the remaining 5 minutes. And people online, bye bye.